Hello students, so now we are going to go with the design of XOR gate using NAND gates. So in the previous lecture, we have already discussed how to make our AND gate, OR gate, NOR gate and NOT gate using our NAND gate. So in this lecture, we are going to go with our XOR gate. So before going for the XOR gate, we should know that how we are going to connect the NAND gates to get our XOR gate. So let's start with the output of the XOR gate only, that is equal to A bar B plus AB bar. Everybody knows it, and how you write it? You write it as this. So you all know the basic operations of Boolean, that is if 0 multiplied by 1, then the output is 0, and if 1 is multiplied by 0, the output is again 0. Or in other words, if I say that if A is multiplied with its complement, the output is 0, and if B is multiplied with B bar, the output is 0. So what if I say that I am going to add a 0 here, and I am going to add a 0 with this term? Does adding 0 make any difference? No. So I am going to replace my this 0 with B bar. This becomes A bar B, and similarly I am going to replace the next 0 with A bar. So taking my this B common from these both and taking A common from these both, what I am going to get is, taking B out, I'm going to get A bar plus B bar inside. Similarly, taking A out, I'm going to get again A bar plus B bar inside. Because I have to implement my this connection using NAND, so all the plus signs are to be changed with a multiplication sign or with a dot sign. So what you need to know is, you all need to remember that De Morgan's rule give you that if AB whole bar is there, it is equal to A bar plus B bar and vice versa. So that means if I have got A bar plus B bar here, I can replace it with this thing. So I am just going to replace my this thing with B into AB whole bar. Similarly, A into AB whole bar. So the next thing that I need to do is replace my this addition sign. How can I remove this? If you all know that A bar double bar is equal to A only. So that means if I am going to add 2 bars over here and 2 bars over here, it is not going to make any difference. But after doing this, I am again going to apply my this thing. But in this case, my this whole will be equal to A bar and my this whole will be equivalent to B bar. So converting it into A into B whole bar terms, so it is going to provide me A into B whole bar. So that means after starting with my this basic output of XOR gate, what I have got is a complete output that can be implementing using NAND gates. So now what I'm going to do is, I'm just going to rub the whole thing and we are going to just draw the output that we have just taken using our NAND gates. So what I'm going to do now is, I'm going to write my this output again here. So it is equal to B into AB bar, the whole bar. Similarly, A into AB bar, the whole bar and whole bar. So now I am going to implement the same circuit using my gates. So firstly, you can see that here you are getting AB bar and AB bar. So let's first give a gate. This is your NAND gate, and I have given it A and B here. That is giving me the output as AB whole bar. Now this AB whole bar will be acting as the input to the next gate, NAND gate. And you can see that the next gate has got B as the other input. So that means you have got B as the next input, and similarly you have got A as the other input over here. So that means what you are going to get over here in the next step, it will be A into AB bar, the whole bar. Similarly, B into AB bar, the whole bar. And then you need to perform your this bar operation and this product operation. So that means your these both are going to act as the input to the last stage of your NAND gate. So that means now you require 4 NAND gates to implement this on Tinkercad. So now let's go to Tinkercad and do it step by step. So here you can see that I have not made any connections right now here. What I have done is, let me just delete this one also. So now what we are going to do is, this is my VCC, this is VCC, and this is my ground. So firstly, I have to go with my A and B inputs to my 2 different gates. So let's say this is my first gate and this is the input to this A. And now this is my second gate and this is my input B here. So the other input that is coming to this is from your this gate. So this gate is also getting your A as the input to 1 here and B as the input to other. And the output that is coming here is acting as the input to this gate, as well as it is acting as the input to your this gate. Output that is coming here is acting as the input. Or I can put it here. Right? So it is acting as the input, and now the output from here is acting as the input to this one, and the output from here is acting as the second input to your this gate, and the final output of your this gate is going to the anode of the LED. So now this is your XOR gate. Now coming on to the output of the XOR gate, the XOR gate only gives you the output when both inputs are of different format. Like, let's start with the simulation. So for both 0, it is coming out to be high. This is coming out to be high again. This is coming out to be not working here. So that means there is some problem in the connection. And for that, we have to check out for every input that is coming. Let me just recollect all the things. So there was a little bit of error here. What I did was I took my this lead towards 13. In actual, it should have been on 14th, because what I did was I gave number 1 and number 2 on the same switch. That is why it was showing like this. So now we come on to the simulation part. Only this is the change that I have made and my circuit is working now. So here you go with, so when 0 and 1 is there, my LED is blinking. When both are 1, LED is stopped working. When 1 and 0 is there, again it is on. And when both are 0, my LED is not working. So this is the truth table of the XOR gate that we have implemented. Once again, you can see that for both inputs to be different, only then the output is high. Similarly, when my number 2 pin is high and 1 is low, only then my this LED is working. Otherwise, for both high or both low, my this LED is low. So this proves my XOR. So that's all for now. But when you are making the connections, just be very careful, because you have to remember that this first pin is of VCC. So sometimes we, like, what I did was I actually counted like 1, 2, and this is my this third one. So that's why the mistake happened. So this is how you prove your XOR gate and design it. So that's all for now. Thanks for watching the video.